We've now met a whole toolbox of algorithms: nearest neighbors, trees, forests, boosting, support vector machines, and naive Bayes. So here's the natural question. Faced with a new problem, which one should you actually pick? Let's build a simple way to decide. First, the honest truth. There is no single best algorithm. Researchers even have a name for this: the no free lunch theorem. The best choice always depends on your data, your goal, and your constraints. Let's line them up side by side, each with its superpower and its main watchout. Nearest neighbors is simple but slow. Trees are readable but wobbly. Forests and boosting are accurate but heavier. Support vector machines love clean margins, and naive Bayes is a lightning-fast text specialist. To narrow it down, ask a few questions about your problem. How much data do you have? Do you need to explain each decision? Is it tables of numbers or text? And how much time do you have to train and predict? Your answers point you toward the right tool. Here are some handy rules of thumb. For everyday tables of numbers, start with a random forest or gradient boosting. For text, reach for naive Bayes. When you need to explain the model, use a single small tree, and always keep logistic regression as a simple, strong baseline. But rules of thumb are only a starting point, never the final word. Always begin with a dead simple baseline, like always predicting the most common class. If a fancy model can't clearly beat that baseline, it isn't earning its keep. And when you do compare models, compare them fairly. Same data split, same cross-validation, same metric for everyone, exactly like we learned in Module 5. Only then can you trust which model is truly best. That's exactly what our project does. We take a lone risk dataset and put our algorithms in a fair contest. Split the data, set a baseline, then cross-validate each model on the very same folds. The winner earns one, and only one, final test on the sealed test set. In code, it's beautifully uniform. We put each model in a dictionary. Then we loop over them, running the same cross-validation on each and collecting the scores. Because every model shares the import-fit-predict pattern, comparing them is almost effortless. So, there's no universal best. Match the algorithm to your data and your needs, start from a baseline, and compare fairly. The guided notebook walks you through the whole lone risk contest, step by step. Next, we'll ask a deeper question. Which features is the model actually using?